है एवरीवन, वेलकम टू एनसीईआरटी ऑडियो बुक। आज हम लोग पढ़ेंगे एस ब्लॉक एलिमेंट्स। द फर्स्ट एलिमेंट ऑफ एल्कली एंड अल्कलाइन अर्थ मेटल्स डिफर्स इन मेनी रेस्पेक्ट्स फ्रॉम अदर मेंबर्स ऑफ द ग्रुप. The S block elements of the periodic table are those in which the last electron enters the outermost s orbital. As the s orbital can accommodate only two electrons, two groups 1 and 2 belong to the S block of the periodic table. The group 1 of periodic table consists of the elements lithium, sodium, potassium, rubidium, cesium and francium. They are collectively known as the alkali metals. These are so called because they form hydroxides on reaction with water, which are strongly alkaline in nature. The elements of group 2 include beryllium, magnesium, calcium, strontium, barium and radium. These elements, with the exception of beryllium, are commonly known as the alkaline earth metals. These are so called because their oxides and hydroxides are alkaline in nature, and these metal oxides are found in the earth's crust. Among the alkali metals, sodium and potassium are abundant, and lithium, rubidium and cesium have much lower abundances. Francium is highly radioactive. Its longest-lived isotope, francium-223, has a half-life of only 21 minutes. Of the alkaline earth metals, calcium and magnesium rank 5th and 6th in abundance, respectively, in the Earth's crust. Strontium and barium have much lower abundances. Beryllium is rare and radium is the rarest of all, comprising only 10 to the power minus 10% of igneous rocks. The general electronic configuration of S block elements is noble gas Ns1 for alkali metals and noble gas Ns2 for alkaline earth metals. Lithium and beryllium, the first elements of group 1 and group 2 respectively, exhibit some properties which are different from those of the other members of the respective group. In these anomalous properties, they resemble the second element of the following group. Thus, lithium shows similarities to magnesium and beryllium to aluminium in many of their properties. This type of diagonal similarity is commonly referred to as diagonal relationship in their periodic table. The diagonal relationship is due to the similarity in ionic sizes and or charge upon radius ratio of the elements. Monovalent sodium and potassium ions and divalent magnesium and calcium ions are found in large proportions in biological fluids. These ions perform important biological functions such as maintenance of ion balance and nerve impulse conduction. 10.1 Group 1 elements alkali metals. The alkali metals show regular trends in their physical and chemical properties with the increasing atomic number. The atomic, physical and chemical properties of alkali metals are discussed below. Electronic configuration. All the alkali metals have one valence electron Ns1 outside the noble gas core. The loosely held s electron in the outermost valence shell of these elements makes them the most electropositive metals. They readily lose electron to give monovalent M+ ions, hence they are never found in free state in nature. Atomic and ionic radii. The alkali metal atoms have the largest sizes in a particular period of the periodic table. With increase in atomic number, the atom becomes larger. The monovalent ions are smaller than their parent atom. The atomic and ionic radii of alkali metals increase on moving down the group, that is, they increase in size while going from lithium to cesium. 10.1.3 Ionization enthalpy. The ionization enthalpies of alkali metals are considerably low and decrease down the group from lithium to cesium. This is because the effect of increasing size outweighs the increasing nuclear charge and the outermost electron is very well screened from the nuclear charge. Hydration enthalpy. The hydration enthalpies of alkali metal ions decrease with increase in ionic sizes. Li plus has maximum degree of hydration, and for this reason lithium salts are mostly hydrated. Example, LiCl twice H2O. Physical properties. All the alkali metals are silvery white, soft and light metals. Because of the large size, these elements have low density which increase down the group from lithium to cesium. However, potassium is lighter than sodium. The melting and boiling points of the alkali metals are low, indicating weak metallic bonding due to the presence of only a single valence electron in them. The alkali metals and their salts impart characteristic color to an oxidizing flame. This is because the heat from the flame excites the outermost orbital electron to a high energy level. When the excited electron comes back to the ground state, there is emission of radiation in the visible region of the spectrum. Alkali metals can therefore be detected by the respective flame test and can be determined by flame photometry or atomic absorption spectroscopy. These elements, when irradiated with light, the light energy absorbed may be sufficient to make an atom lose electron. This property makes cesium and potassium useful as electrodes in photoelectric cells. 10.1.6 Chemical Properties. The alkali metals are highly reactive due to their large size and low ionization enthalpy. The reactivity of these metals increases down the group. 1. Reactivity towards air. The alkali metals tarnish in dry air due to the formation of their oxides, which in turn react with moisture to form hydroxides. They burn vigorously in oxygen, forming oxides. Lithium forms monoxide, sodium forms peroxide, the other metals form superoxides. The superoxide O2- ion is stable only in the presence of large cations such as potassium, rubidium, cesium. In all these oxides, the oxidation state of the alkali metal is +1. Lithium shows exceptional behavior in reacting directly with nitrogen of air to form nitride Li3n as well. Because of their high reactivity towards air and water, alkali metals are normally kept in kerosene oil. Reactivity towards water. The alkali metals react with water to form hydroxide and dihydrogen. It may be noted that although lithium has most negative E0 value, its reaction with water is less vigorous than that of sodium, which has the least negative E0 value among the alkali metals. This behavior of lithium is attributed to its small size and very high hydration enthalpy. Other metals of the group react explosively with water. They also react with proton donors such as alcohol, gaseous ammonia, and alkynes. 3. Reactivity towards dihydrogen. The alkali metals react with dihydrogen at about 673 Kelvin, lithium at 1073 Kelvin to form hydrides. All the alkali metal hydrides are ionic solids with high melting points. 4. Reactivity towards halogens. The alkali metals readily react vigorously with halogens to form ionic halides M plus X minus. However, lithium halides are somewhat covalent. It is because of the high polarization capability of lithium ion. The distortion of electron cloud of the anion by the cation is called polarization. The Li plus ion is very small in size and has high tendency to distort electron cloud around the negative halide ion. Since anion with large size can be easily distorted among halides, lithium iodide is the most covalent in nature. Reducing nature. The alkali metals are a strong reducing agent, lithium being the most and sodium the least powerful. The standard electrode potential E0, which measures the reducing power, represents the overall change. With the small size of its ion, lithium has the highest hydration enthalpy, which accounts for its high negative E0 value and its high reducing power. 6. Solutions in liquid ammonia. The alkali metals dissolve in liquid ammonia, giving deep blue solutions which are conducting in nature. The blue color of solution is due to the ammoniated electron, which absorbs energy in the visible region of light and thus imparts a blue color to the solution. The solutions are paramagnetic and on a standing slowly liberate hydrogen, resulting in the formation of amide. In concentrated solution, the blue color changes to bronze color and becomes diamagnetic. Uses. Lithium metal is used to make useful alloys, for example with lead to make white metal bearings for motor engines, with aluminium to make aircraft parts, and with magnesium to make armor plates. It is used in thermonuclear reactions. Lithium is also used to make electrochemical cells. Sodium is used to make a sodium-lead alloy needed to make PbEt4 and PbMe4. These organolead compounds were earlier used as anti-knock additives to petrol, but nowadays vehicles use lead-free petrol. Liquid sodium metal is used as a coolant in fast breeder nuclear reactors. Potassium has a vital role in biological systems. Potassium chloride is used as a fertilizer. Potassium hydroxide is used in the manufacture of soft soap. It is also used as an excellent absorbent of carbon dioxide. Cesium is used in devising photoelectric cells. 10.2 General characteristics of the compounds of the alkali metals. All the common compounds of the alkali metals are generally ionic in nature. General characteristics of some of their compounds are discussed here. Oxides and hydroxides. On combustion in excess of air, lithium forms mainly the oxide Li2O plus some peroxide Li2O2. Sodium forms the peroxide Na2O2 and some superoxide NaO2, whilst potassium, rubidium and cesium form the superoxides MO2. Under the appropriate conditions, pure compounds M2O, M2O2 and MO2 may be prepared. The increasing stability of the peroxide or superoxide as the size of the metal ion increases is due to the stabilization of large anions by larger cations through lattice energy effects. These oxides are easily hydrolyzed by water to form the hydroxides according to the following reactions. The oxides and the peroxides are colorless when pure, but the superoxides are yellow or orange in color. The superoxides are also paramagnetic. Sodium peroxide is widely used as an oxidizing agent in inorganic chemistry. The hydroxide, which are obtained by the reaction of the oxides with water, are all white crystalline solids. The alkali metal hydroxides are the strongest of all bases and dissolve freely in water with evolution of much heat on account of intense hydration. Halides. The alkali metal halides MX are all high melting, colorless crystalline solids. They can be prepared by the reaction of the appropriate oxide, hydroxide or carbonate with aqueous hydrohalic acid. All of these halides have high negative enthalpies of formation. The delta H of formation values for fluorides become less negative as we go down the group, whereas the reverse is true for delta H formation for chlorides, bromides and iodides. For a given metal, delta H formation always becomes less negative from fluoride to iodide. The melting and boiling points always follow the trend: fluoride greater than chloride, greater than bromide, greater than iodide. All these halides are soluble in water. The low solubility of LiF in water is due to its high lattice enthalpy, whereas the low solubility of CSI is due to smaller hydration enthalpy of its two ions. Other halides of lithium are soluble in ethanol, acetone and ethyl acetate. LiCl is soluble in pyridine also. Salts of oxoacids. Oxoacids are those in which the acidic proton is on a hydroxyl group which an oxo group attached to the same atom. Example: carbonic acid H2CO3, sulfuric acid H2SO4. The alkali metals form salts with all the oxoacids. They are generally soluble in water and thermally stable. Their carbonates M2CO3 and in most cases the hydrogen carbonates MsCO3 also are highly stable to heat. As the electropositive character increases down the group, the stability of the carbonates and hydrogen carbonates increases. Lithium carbonate is not so stable to heat. Lithium, being very small in size, polarizes a large CO3 2- ion, leading to the formation of more stable Li2O and CO2. Its hydrogen carbonate does not exist as a solid. 10.3 Anomalous properties of lithium. The anomalous behavior of lithium is due to the exceptionally small size of its atom and ion, and 2 high polarizing power, that is charge upon radius ratio. As a result, there is increased covalent character of lithium compounds, which is responsible for their solubility in organic solvents. Further, lithium shows diagonal relationship to magnesium, which has been discussed subsequently. 10.3.1 Points of difference between lithium and other alkali metals. Lithium is much harder. Its melting point and boiling point are higher than the other alkali metals. Lithium is least reactive but the strongest reducing agent among all the alkali metals. On combustion in air, it forms mainly monoxide Li2O and the nitride Li3N, unlike other alkali metals. 3. LiCl is deliquescent and crystallizes as a hydrate. LiCl twice H2O, whereas other alkali metal chlorides do not form hydrates. 4. Lithium hydrogen carbonate is not obtained in the solid form, while all other elements form solid hydrogen carbonates. Lithium, unlike other alkali metals, forms no ethanide on reaction with ethine. 6. Lithium nitrate, when heated, gives lithium oxide Li2O, whereas other alkali metal nitrates decompose to give the corresponding nitride. 7. LiF and Li2 are comparatively much less soluble in water than the corresponding compounds of other alkali metals. 10.3.2 Points of similarities between lithium and magnesium. The similarity between lithium and magnesium is particularly striking and arises because of their similar sizes. Atomic radii lithium बराबर 152 picometer, magnesium is equal to 160 picometer, ionic radii Li plus is 76 picometer and Mg2 plus is equal to 72 picometer. The main points of similarity are: 1. Both lithium and magnesium are harder and lighter than other elements in their respective groups. 2. Lithium and magnesium react slowly with water. Their oxides and hydroxides are much less soluble, and their hydroxides decompose on heating. Both form a nitride, Li3n and Mg3n2, by direct combination with nitrogen. 3. The oxides Li2 and MgO do not combine with excess oxygen to give any superoxide. 4. The carbonates of lithium and magnesium decompose easily on heating to form the oxides and CO2. Solid hydrogen carbonates are not formed by lithium and magnesium. Both LiCl and MgCl2 are soluble in ethanol. Both LiCl and MgCl2 are deliquescent and crystallize from aqueous solution as hydrates. LiCl twice H2 and MgCl2 dot at H2O. 10.4 Some important compounds of sodium. Industrially important compounds of sodium include sodium carbonate, sodium hydroxide, sodium chloride, and sodium bicarbonate. The large scale production of these compounds and their uses are described below. Sodium carbonate, washing soda, Na2CO3.10H2O. Sodium carbonate is generally prepared by Solvay process. In this process, advantage is taken of the low solubility of sodium hydrogen carbonate, whereby it gets precipitated in the reaction of sodium chloride with ammonium hydrogen carbonate. The latter is prepared by passing CO2 to a concentrated solution of sodium chloride saturated with ammonia, where ammonium carbonate followed by ammonium hydrogen carbonate are formed. The equations for the complete process may be written as: sodium hydrogen carbonate crystal separates. These are heated to give sodium carbonate. In this process, ammonia is recovered when the solution containing NH4Cl is treated with calcium hydroxide. Calcium chloride is obtained as a byproduct. It may be mentioned here that Solvay process cannot be extended to the manufacture of potassium carbonate because potassium hydrogen carbonate is too soluble to be precipitated by the addition of ammonium hydrogen carbonate to a saturated solution of potassium chloride. Property: sodium carbonate is a white crystalline solid which exists as decahydrate Na2CO3.10H2. This is also called washing soda. It is readily soluble in water. On heating, the decahydrate loses its water of crystallization to form monohydrate. Above 373 Kelvin, the monohydrate becomes completely anhydrous and changes to a white powder called soda ash. Carbonate part of sodium carbonate gets hydrolyzed by water to form an alkaline solution. Uses: it is used in water softening, laundering, and cleaning. It is used in manufacture of glass, soap, borax, and caustic soda. 3. It is used in paper, paints, and textiles industries. 4. It is an important laboratory reagent both in qualitative and quantitative analysis. Sodium chloride, NaCl. The most abundant source of sodium chloride is seawater, which contains 2.7 to 2.9% by mass of salt. In tropical countries like India, common salt is generally obtained by evaporation of seawater. Approximately 50 lakh tons of salt are produced annually in India by solar evaporation. Crude sodium chloride, generally obtained by crystallization of brine solution, contains sodium sulfate, calcium chloride, and magnesium chloride as impurities. Calcium chloride CaCl2 and magnesium chloride MgCl2 are impurities because they are deliquescent, absorb moisture easily from the atmosphere. To obtain pure sodium chloride, the crude salt is dissolved in minimum amount of water and filtered to remove insoluble impurities. The solution is then saturated with hydrogen chloride gas. Crystals of pure sodium chloride separate out. Calcium and magnesium chloride, being more soluble than sodium chloride, remain in solution. Sodium chloride melts at 1081 Kelvin. It has a solubility of 36 gram in 100 gram of water at 273 Kelvin. The solubility does not increase appreciably with increase in temperature. Uses: 1. It is used as a common salt or table salt for domestic purpose. 2. It is used for the preparation of Na2O2, NaOH and Na2CO3. Sodium hydroxide, caustic soda, NaOH. Sodium hydroxide is generally prepared commercially by the electrolysis of sodium chloride in Kastner-Kellner cell. A brine solution is electrolyzed using a mercury cathode and a carbon anode. Sodium metal discharged at the cathode combines with mercury to form sodium amalgam. Chlorine gas is evolved at the anode. The amalgam is treated with water to give sodium hydroxide and hydrogen gas. Sodium hydroxide is a white translucent solid. It melts at 591 Kelvin. It is readily soluble in water to give a strong alkaline solution. Crystals of sodium hydroxide are deliquescent. The sodium hydroxide solution at the surface reacts with the CO2 in the atmosphere to form Na2CO3. Uses: it is used in the manufacture of soap, paper, artificial silk and a number of chemicals, in petroleum refining, in the purification of bauxite, in the textile industries for mercerizing cotton fabrics, for the preparation of pure fats and oils, and as a laboratory reagent. Sodium hydrogen carbonate, baking soda, NaSO3. Sodium hydrogen carbonate is known as baking soda because it decomposes on heating to generate bubbles of carbon dioxide, leaving holes in cakes or pastries and making them light and fluffy. Sodium hydrogen carbonate is made by saturating a solution of sodium carbonate with carbon dioxide. The white crystalline powder of sodium hydrogen carbonate, being less soluble, gets separated out. Sodium hydrogen carbonate is a mild antiseptic for skin infections. It is used in fire extinguishers. 10.5 Biological importance of sodium and potassium. A typical 70 kg man contains about 90 gram of sodium and 170 gram of potassium, compared with only 5 gram of iron and 0.06 gram of copper. Sodium ions are found primarily on the outside of cells, being located in blood plasma and in the interstitial fluid which surrounds the cells. These ions participate in the transmission of nerve signals, in regulating the flow of water across cell membranes, and in the transport of sugars and amino acids into cells. Sodium and potassium, although so similar chemically, differ quantitatively in their ability to penetrate cell membranes, in their transport mechanisms, and their efficiency to activate enzymes. Thus, potassium ions are the most abundant cations within cell fluids, where they activate many enzymes, participate in the oxidation of glucose to produce ATP, and with sodium are responsible for the transmission of nerve signals. There is a very considerable variation in the concentration of sodium and potassium ions found on the opposite sides of cell membranes. As a typical example, in blood plasma, sodium is present to the extent of 143 millimole per liter, whereas the potassium level is only 5 millimole per liter within the red blood cells. These concentrations change to 10 millimole Na plus and 105 millimole K plus. These ionic gradients demonstrate that a discriminatory mechanism called the sodium-potassium pump operates across the cell membrane, which consumes more than one-third of ATP used by a resting animal and about 15 kg per 24 hour in a resting human. That's all for today. Thanks for listening. Group 2 elements in the next video.